Thank you, Sasha, for the introduction. Good evening, ladies and gentlemen, everyone. It is a pleasure for me to be here today in this important event, in this important summit, with the vision shaping the future of cooling together. So in this opportunity, I would like to give some introduction about our approach in utilizing this CO2 that aligns with this vision, utilizing the CO2 as one of natural refrigeration or natural refrigerant. So first we will start by explaining why natural refrigerants are so essential, and then we will dive into CO2 solutions, our CO2 solutions, which are actually utilizing the hot side and also cold side of CO2 refrigeration technologies or refrigeration cycle, which was already actually explained by Mr. Chia in this morning. So I would like just give some review or maybe some another point of view explanation. Okay. So we will start first why these natural five are so efficient. We actually begin our commitments with this natural five philosophy. The natural five contains of the ammonia, CO2, hydrocarbon, water, and air are actually what we believe will define and make a big contribution to the future of cooling or refrigeration. And the key features of these natural five are undeniable and so essential for the sustainability. They are natural refrigerants, which means they exist in the nature. They are not chemically synthesized. They have a high efficiency characteristic, which means if we are using these high efficiency characteristics, it will make a big impact, it will make a direct impact to the operating expenses reduction, which I believe will make most of us be happy. They have also zero ODP and also low GWP, and by using this characteristic, it will have less impact to the environment. As can we see in the graph, our approach, Mayekawa approach, in utilizing these natural five, these natural refrigerant is comprehensive. Each natural refrigerant is supported by one dedicated product line that enforces this strategy. Okay, next, let's talk more about CO2 as one of natural refrigeration, one of natural refrigerant. So by using this CO2 as one of natural refrigerant, we will have at least three benefits that can be achieved by using this CO2 as one of natural refrigerant. First, we will have an environmental friendly and safe benefit. If we are talking about the CO2 heat pumps concept, as I informed you before, it's already explained actually in this morning and some speaker before me. So because we eliminate the combustion process, so we will have a system, the system will be safe and it will be NOx-free. It is one of the benefits we can achieve if we are using CO2 as one of natural refrigeration. The second one is from the economic point of view. We see a potential of up to 50% energy consumption reduction. And again, if we are talking about the CO2 pump, CO2 heat pump concept, there will be a significant additional merits when heating and cooling are being used in the same time, simultaneously, because we will have a higher COP at the time. Then the third one is the reliability point of view. The system are being from proven and reliable CO2 technology, heat technology refrigeration, which ensures longer life cycle costing and also the automatic operation across a broad temperature range. Okay, we already talked about the CO2 as natural refrigeration. Now let me talk about our product, which is actually one of the CO2 heat pump concept. First one is the Unimo AW. This is a Unimo series from our product. First one is the Unimo AW. AW actually means the air to water. So we are using air as a heat source to produce hot water. So basically the basic specification of this product, so we can supply plus 65 degrees of hot water or maybe 90 degrees of hot water, depending on the requirement from the end user. Heating capacity is around 80 kilowatt. Actually, this depends on the inlet temperature of water and also the outlet temperature of hot water. And the coefficient of performance, COP, can be achieved, the value of 4.2 can be achieved, which is quite high for the heating system. Another features that can be achieved from this machine is we can cut energy costs, and also we can reduce CO2 footprint. And again, as I informed you before, there will be no combustion, so the system will be safe and free of NOx. And around about the heating capacity, as I informed you before, actually the heating capacity is we can achieve until 100 kilowatt, depending on the temperature, inlet temperature, and also outlet temperature. And because we are using 25 kilowatt motor, so we can achieve this around 4 COP, which is quite high for the heating system. This is the scheme of Unimo. So as can be seen here, so we are using the city water, which has temperature is the raw water temperature. We are using this as an inlet water. So we will produce here to make 65 or 90 degrees of hot water. Okay, next one is Unimo WW. So the last one before it was AW, now it is WW. WW actually means water to water. So we are using water as a heat source to produce hot water. Same as before, the hot water that can be produced, the temperature is 65 or 90 degrees, depending on the requirement from user. And at the same time, we can produce cold water or chilled water from minus 9 degrees to plus 32 degrees, again, depending on the requirement from user. And because we have the same capacity as before, the heating capacity is 100 kilowatt, so we can have the total COP if we add the heating COP and also the cooling COP. The total COP can be the achieved total COP can be like 9.3, which is quite high for this system. And same as before also, because this is this will make a hot water and chilled water together, so we can integrate both function of boiler or heater, because we will produce hot water, and we can also integrate chiller, because we will produce cold water or chilled water. So this is the scheme of the application when we use this product. As can be seen here, we use city water with raw temperature, ambient temperature, and then we will produce 65 or 90 degrees of hot water. But at the same time, we also can produce chilled water or cold water, depending on the requirement from customer or from user. Another scheme that can be used from this product, this is the same. So we are using water supply. We are using city water to produce a hot water 65 to 90 degrees. But at the same time, we are using that one. We are using the wasted heat from the wastewater as a heat recovery, and the temperature will be from 70 to 37 degrees to 12 degrees. Another scheme is like this. So we are using the unused energy as a heat source. So in this time, let's say we can use groundwater or maybe geothermal heat as the heat source, and then we will produce that hot water 65 or maybe 90 degrees, and at the same time, we also can produce 20 degrees of cold water or maybe 5 degrees of cold water at the same time, actually. So we can achieve the high COP, as I told you before. It can achieve 9 the value of COP. Okay. Okay, the next product is Unimo AWW. So at first it was Unimo AW, and then Unimo WW, and then now it's Unimo AWW. Actually, this is the combination of Unimo AW and Unimo WW. So we will have air source mode and also water source mode, depending on the condition at the time. So this also will generate the hot water, and the scheme when we use this product is like this. So when let's say it is a daytime or maybe summer, because we need to cool this room, let's say we will cool this room by using air handling unit that is using cold water or chilled water, let's say maybe 15 degrees or 10 degrees. We use this product with water heat source mode. So we will produce hot water, as I explained before. We can produce until 90 degrees. And at the same time, we also can make a cold water or chilled water like 99 degrees or maybe 15 degrees to cool this room. And this is for daytime or summer. And if it is nighttime or winter, we don't need to cool this room. We don't need to produce any cold water. We don't need to produce any chilled water. So in this case, we just switch over the mode from water source to air source. So we will only produce the hot water until maybe 90 degrees. So this is like the flexibility of this machine. We can use air source mode, we can use water source mode, and it can be switched over automatically. We can just add the program to switch it over automatically. Okay, so next machine is EcoSirocco. EcoSirocco is basically the same with Unimo. The main difference is in Unimo, we produce hot water. And in this EcoSirocco, we produced hot air. And not only we produce the hot air, but at the same time, because this is a water source heat pump, so we also can produce cold water or chilled water. The hot air can be produced is until 120 degrees, and then it can be sent to the application that needs this 120 degrees of hot air. One of the application is like this. During the painting process, for example, during the painting process, like maybe the cars or maybe some parts of maybe automatic parts, it needs heating and also cooling at the same time. It needs drying process, and after that, it also needs the cooling process. So we can apply this machine into this application, into this painting application. So let's say we have our machine here, and then we will send, let's say ambient air is 20 degrees. We can produce until 120, then it can be sent to the heating or drying process. And at the same time, because we can produce 7 degrees of chilled water, this will be sent to the next process, which is a cooling process after the heating. By using this machine, by using this application, we can reduce or maybe replace the heater, the boiler, or maybe if some customer using gas burner which is using heater, it also can be replaced. And at the same time, the water chiller also can be reduced. The workload, the heat load of water chiller also can be reduced, or maybe can be replaced. So this is one of the application of this EcoSirocco. Next is I want to talk about our another product, which is we are calling this as a crease system. So crease system is basically same as before. It is using a CO2 heat pump inside this unit to cool down the air and also to heating up the air. But the difference is in this crease, it is a desiccant dehumidifier. So there is a desiccant rotor inside this machine. The dehumidification can be achieved in this machine. So we can achieve the low humid air in low temperature. So as we know, basically the hurdle of this system is if we want to have a low humid air, it is difficult to control the temperature. So by using this CRIS CO2 desiccant dehumidifier, we can have low humid air in low temperature room. And since drying is also possible even in low temperature environments, the occurrence of mold and rust is curtailed. And we can see the reduced energy consumption of 50% has been achieved compared to the conventional desiccant humidifiers, the dehumidifiers. And it is a safe, natural CO2, which has, as I informed before, it has a low ODP, 0 ODP actually, and with 1 GWP value. So it is actually safe for the environment. So what is inside the CRIS? Inside the CRIS is like this. So as I informed before, we have a CO2 heat pump here, which we have the cooling side and also heating side, but we also add the desiccant rotor here. So this is the inside the room, this is the outdoor, so this is indoor, outdoor. The water contained from outdoor area, from outside, will be sent to the machine, and then the water contained in the air will be absorbed in this desiccant rotor. Then after that, it will be sent to the CO2 heat pump to be cooled down, and then it has the low temperature. Let's say here there are 3 water content here, and then it will be sent to the machine. 2 of these 3 will be absorbed in this desiccant rotor, and only one water content being sent into the room, so we can achieve the low humidity of low temperature room. And also the reverse is the same. So the water, the air inside the room will be sent again to this machine, to this unit, and it will go through the heater. Heater is actually the condenser in CO2 heat pump concept. And then it will take the 2 water content here, and then it will go out the outdoor area. So let's say there are 3 water content here, and then it will be heated up, and then we'll go to this desiccant rotor. It will take these 2, so the water content will become 5. This is actually the basic mechanism inside this machine, inside this CRIS unit, so we can achieve low humidity in low temperature room. Okay, if we want to compare the electric or power consumption by using this CRIS and conventional one, we can get the 75% reduction of power consumption. This calculation is basically based on our technical sheet. So one CRIS, we have a heating capacity is 70.9 kilowatt, with the cooling capacity is 50 kilowatt, and our input power is 20.9 kilowatt. By using this assumption, as I informed you before, we will have a 75% reduction of power consumption. The explanation is like this. If we are using the electric heater, which is the conventional one, we will need 70.9 kilowatt because our heating capacity is 70.9. And also at the same time, we will need a chiller, which has the power consumption. If we assume the COP of the electric chiller is 3.3, so we will have the 14.3 kilowatt of power consumption. So that's why if we compare the conventional one and our unit, the power consumption can be reduced up to 70%, 75%. Okay? This is the actual case in our customer. So before we adopting this CRIS unit, the inside the production room, it has a high humidity of air and also wet condition. And after adopting this CRIS unit, we can see, as we can see here, it is dry and also with a low humidity of air. This is one of the actual case in our customer. Okay, so up until now, I have explained about our product, our system that is using CO2 as primary refrigerant. And now I want to talk about our product that is using CO2 not as primary refrigerant, but as a secondary refrigerant. So because we are using CO2 as a secondary refrigerant, of course, we will need a primary refrigerant. So the refrigerant we are using as a primary refrigerant is still the same natural refrigerant, which is ammonia. Ammonia is already explained by previous speakers. It's still the king in the refrigeration. So we utilize this characteristic to improve and to develop this machine. So this is our machine. We are calling this as a Newton. So we are using CO2 as a secondary refrigerant. That CO2 will be sent to the indoor, and the ammonia, which has a less charging or minimum charging, only being used inside the machine room. So we can minimize the contamination to the product if there is any leakage. Okay, so as we know, more than 70% of electricity used in cold storage is used by the cooling equipment. By using this Newton equipment, we can have the reduction of power consumption up to 50%. We can have up to 50% by using this Newton product. Then I would like to now talk about the Newton basic concept. This is the basic concept of our product. So as I informed before, this is our machine, and this is actually the machine room area, and this is the indoor area or inside the cold storage. Our Newton is only here, and the green line shows the ammonia line is only in machine room. So the ammonia will be sent to the condenser. Our condenser is the water-cooled condenser, so we still need the cooling tower to cool down the ammonia. And then it will go to the expansion valve, and then will go to the evaporator to cool down the CO2. Let's say our ammonia temperature is minus 35 degrees. It will cool down the CO2 until minus 32 degrees. Then this CO2 will be sent to the cold storage. Again, as I informed you before, we can minimize the risk of contamination of ammonia to the product, just in case any leakage. And as I informed you before, we have a minimum charging. So it's only 28 grams per US RT. Sometimes only like 20 or 21 kgs of ammonia need to be used. Next, I would like to explain and show you the comparison between ammonia CO2 brine and cascade system. So the red one is our ammonia system's COP. Oh, by the way, the vertical line is COP and the horizontal line is the CO2 temperature. This is our Newton COP, and the green one is the CO2 brine COP. This is also actually using our compressor, and the blue line is the cascade COP. This is also same, are using our compressor. As can be seen here, for all the CO2 temperature from minus, let's say minus 27 to minus 43 maybe, all of these CO2 temperature, we can achieve the highest COP if we are using Newton. Especially, it accelerates and exerts its power even more when CO2 temperature falls below minus 35 degrees. However, in general, if we just want to see from these two comparisons, the ammonia CO2 cascade system has a better COP at a temperature below minus 41.5 degrees. Okay, next, I also want to show you about the comparison of COP by refrigerant and system. This vertical line is a COP, and the horizontal line is the average temperature of that area. So this green one is the ammonia CO2 brine, water cooled, and the blue line is the CO2 DX, which is the CO2 transcritical system. This blue, the light blue, is the freon screw system, and this is the light blue actually maybe. Yeah. This is a HFO system. So if we are talking about if we talk about like Jakarta or maybe Bali, which has the average temperature like 27 or maybe 28 degrees, using this green system will achieve a higher COP. But this is only in case of minus 25 degrees. However, if we are talking about plus 5 degrees, this ammonia CO2 brine, which needs a water cooled, will make a lower COP according to the increasing of temperature. Let's say Jakarta is here, or maybe I believe Bali is also around here. It is not recommended to use ammonia CO2 brine water cooled. From this graph, it is recommended to use this CO2 DX or air cooled. Okay. Next is our product again, but actually this is not using CO2 as refrigerant, so let me skip this one. I would just want to show you that this system, we call this Pascal air, can achieve minus 100 degrees of room temperature. And this is not using CO2 as I informed before, this is using air as a refrigerant. This is actually the mechanism of this unit, but let me skip this time because I already run out of the time. But if you have any question or maybe something that you want to discuss, something that you want to ask, you can ask me after this. And also, other than me, we have also 7 members from another Mayekawa. We have from Mayekawa Japan, we have here from Mayekawa Malaysia, and also we have him here from Mayekawa Thailand. So we will be more than happy to answer your questions after this. And as a closing remarks, as today's vision is shaping the future of cooling together, so I would like to ask all of us to keep in our mind, let's just shape the future of cooling together. And I hope in the next future, there will be a good collaboration, good cooperation between all companies that are here today. Thank you again, and terima kasih.